Hi guys, in this video I cover binary trees. Here you can see an example of a binary tree. At the top is a root node, and every node in this tree may have only up to 2 children. So 8 has 2 children, 19 and 4. 19 has the children 76 and 55. 55 only has a single child, 92. 4 has only a single child, 83. 83 has 2 children, 31 and 18, and the leaf nodes don't have any children at all. A binary tree is a special kind of tree where each node may have only up to 2 children. The children are typically referred to as left and right child, which may or may not exist. Some nodes in a binary tree may have only a left node child, where other nodes may have only a right child, and the leaf nodes don't have children at all. The minimum number of nodes in a binary tree can be determined based on the height. So for a height h, the minimum number of nodes that a binary tree will have is h plus 1. This would essentially represent a linked list, where each node just has a single child node except for the leaf node. The maximum number of nodes in a binary tree can also be determined based on the height. So for a height h, the maximum number of nodes would be 2 to the power of height plus 1 minus 1. The minimum depth can be determined based on the number of nodes. So for a binary tree, given n, where n is the number of nodes, the minimum depth that the binary tree will have is log n minus 1. And the maximum depth that the binary tree will have is the number of nodes n minus 1. A full binary tree represents essentially a triangle. That means every node has exactly 2 children, except for the leaf nodes, and the leaf nodes are all at the same level. So essentially, when you see a triangle that represents a binary tree, this is a full binary tree. There's also the notion of a complete binary tree. A complete binary tree is essentially a full binary tree, except the last level is not full. And the last level has to be filled from left to right. So if 76 would have just 3 and not 12, this would still be a complete binary tree. If 55 would have a left child, it would also be a complete binary tree. Now 55 would not have a left child, but it would have a right child. That would not be a complete binary tree, because there's a gap in the last level, and the last level has to be filled from left to right. So here you can see a binary tree. This is neither full nor complete. Here you see a full binary tree. Note that every node has exactly 2 children. The leaf nodes are all at the same level, and the leaf nodes obviously do not have any children. And here's an example of a complete binary tree. All nodes have exactly 2 children, except the last level is not full, and the last level is filled from left to right. So as we add nodes, we would have to add them from left to right to maintain a complete binary tree. If we were just to add a node to 83, this would no longer be a complete binary tree, because there would be some nodes missing here. So how do we implement this? We need 2 classes. We need a tree node class and a tree class. The tree node stores a value that can be of any type. And the examples that I'm using, I'm just simply using an integer, but we really could store anything in a tree node. And then it has 2 pointers, a pointer to the left child and a pointer to the right child. Then I have a constructor where I pass in the value that I want to store. I have some helper methods such as has left, has right, which simply check if the left is not null or the right is not null. I have a helper method to check if it's a leaf node, which checks that both left and right are null. And then the size of the tree node, which would count the node, including its descendants, and the height of the node, which would determine the height based on the longest path to its most distant leaf. Then I have the binary tree class. The binary tree has just a single node, which is the root node of the tree. And then it has the functions for adding, removing, containing, and getting the size of the tree, the height of the tree, and clearing the tree. Now, important is when you implement a binary tree that you keep the traversal separate. So the binary tree is a data structure. The traversal is the algorithm that operates on the data structure. And obviously there are many ways to traverse an algorithm. Here you can see some of the most common ways, which are depth-first search and breadth-first search. And depth-first search for a binary tree has preorder, in-order, and post-order traversal. Let's go over these traversal algorithms. So preorder visits a node before visiting the children. And depth-first search means we go into depth first. So the visitation order for preorder would be 8, 19, 76, 3, then backing up, going to 12, backing up, taking the next path, 55, 47, going up, and then on the other side, 4, 83, and 101. This is the visitation order of preorder. Now in order visits one child first, then the node itself, and then the other child. In my example, I visit the left child first, then the node itself, and then the right child. This would result in a visitation order that you see here. So I start at the root. I cannot visit the root first. I have to visit the left child first. I cannot visit this node. I have to visit the left child first. Cannot visit 76. I have to visit the left child first, which is 3. Now I visited the left child, which is null. So I visit 3. Doesn't have a right child. So I get back up to 76. Now I visited the left child already. So I visit 76. So now I have 3, 76. Go to the right child, doesn't have any children. So it's 12. Go back up, go to 19. I visit 19. Go to 55. I can't visit 55 yet. I have to visit the left child first, which is 47. Then go back up to 55. Go back up and have 8 now. And then go to the right child. Now 4, I have to visit the left child first, which is 83. Then I can visit 4 and then 101. This is the output of the in-order depth-first search. Post-order visits the children first, both of the children, before visiting a node itself. So the output here is as you see. So I can't visit the node itself. I have to visit the children first, 19 as well, 76 as well. This is a leaf node, so I output 3, then go back up. I visited one child, but I still have to visit the other child, which is 12. Doesn't have any nodes, so I output 12. Then I go back up. Now I visited both of its children, so I visit 76. Go back up to 19. I visited one child, but not the other child. So I have to go down to 55. I have not visited the children yet, so I go to 47. 47 is a leaf node, so I visit 47. Then I back up to 55 and then 19. Then go to 8. I can't visit 8 yet because I have to visit the children first. So I go to 4. 83. I visit 83. Go back up to 4. Go to 101. Visit 101. And now I visited the children. I can visit 4 and finally 8. So preorder visits the node itself before its children. In order visits one child, then the node, and the other child. And post order visits all the children first before visiting a node. Now depth first search is basically going level by level. Here we visit 8, 19, 4, then 76, 55, 83, 101, and then 3, 12, 47. How do we implement depth first search? We use a stack. How do we implement breadth first search? We use a queue. Now let's look into the performance of binary tree. The performance of binary tree, we have insert, contains, remove, some checks, is empty, clearing the tree, getting the height or the size. All of these are ON. The reason for this is if you consider a binary tree, first of all, a binary tree can have duplicates. There's no structure or organization in the binary tree. So we don't know how to navigate. We would have to visit all the nodes to find a particular node, to remove a particular node. And also in the worst case, where each node just has a single child node, it would be just like a linked list. So in the worst case, you can consider a binary tree as a linked list. I hope you enjoyed this video. Thank you for watching.